functions. So a rational function looks something like this parent equation that we're given, f of x equals 1 over x. So it asks us over here, what is special about x? Well, in this equation, x is the denominator. So it's the denominator. All right, and one special thing just to realize when x is our denominator is that x cannot equal 0. If x equals 0, you would get an undefined solution. So just like with all of the other graphs that we've done in this class, let's go ahead and create a table quick. So for x values, once again, you can select any that you'd like. I'm going to choose -3 through +3. Oh, and I'm actually going to put 0 in the middle here, since as we said before, x cannot equal 0. And we'll see why in a second. So with these x values, let's substitute them into our equation. This is fairly easy. We would have -1/3, 1/2, -1. Anything over 0 is undefined. 1, 1/2, and 1/3. So if we were to graph these points on our graph, we would have -3, -1/3, -2, -1/2, -1, -1. And over here, we would have 1 and 1, 2 and 1/2, 3 and 1/3. And actually, the graphs that this ends up creating looks something like this. So in a way, it kind of looks like two separate exponential functions. So let's go through and answer some of these questions. So first of all, the domain for this graph is essentially going to be all real numbers besides 0. So how you'd answer that would be all real numbers except x cannot equal 0. Because as you head in the negative direction, we have our function. And as we head in the positive direction, we also have our function. Another way that you could write this in interval notation would be -∞ to 0, making sure that you use an open bracket. Then use our and symbol, 0 to +∞. So essentially what this is saying is we can have any number but 0. Same exact thing goes with our range. As we head in the negative direction, we have our function besides at 0, and same goes with the positive direction. And once again, we can also write this in interval notation, just like with our domain. So since we can't have 0 on this graph, that's really going to limit us. We can't have 0 in the x and the y direction. So in that case, we are going to have none for our x-intercepts, and we will also have no y-intercepts. But this is where the asymptotes come into play. So as it says below here, an asymptote is a line that a graph approaches more and more closely, yet will never cross. So horizontally, our graph is never going to cross 0. It'll get really close, but it'll never cross it. So our horizontal asymptote, if we were to draw in this line, the equation for this line is y equals 0. Similarly, with our vertical asymptote, our equation gets really close to the y-axis, yet it will never actually cross it. So the equation for this asymptote is x equals 0. All right, and that is our parent equation. So let's go through and look at some of these steps. So to graph a rational function, the first thing I would do is draw the vertical asymptote. Okay, these are the values that would make the denominator 0 or undefined. So how we would do this is we would set the denominator equal to 0 and we'll solve. Just like I did above, you can draw a dashed vertical line through the x values of the asymptote. Similarly, with the horizontal asymptote, that represents the end behaviors of the graph. So the function may touch or cross the horizontal asymptote. It may actually cross it, but still you will draw a dashed horizontal line through this value. Okay, horizontal asymptotes are determined by the degrees of the exponents in the numerator and in the denominator. So our key detail is our degrees, which is tying back into our previous chapters. So really the key here is if the degree of your numerator is less than the degree of your denominator, in the first case here, the line y equals 0 is the horizontal asymptote. If they are equal, the line y equals your leading coefficient of your numerator over denominator is the horizontal asymptote. But if your numerator is greater than your denominator, there is no horizontal asymptote. All right, so this is a lot to digest. We are going to look at how this works in the next example. Finally, to find the y-intercept, we need to set our equation as y equals 0 and solve for x. And the opposite goes with the y-intercept, where we are going to substitute in 0 for x. Final thing here, we have to find two values to the left of the vertical asymptote and two values to the right. Plot these points and your intercepts, and then draw the general shape of your graph. That is known as a hyperbola. So the shape of the graph that we've created here is considered an hyperbola. Okay, so make sure you pause the video here, copy down all of this info. I know it is a ton of writing, but it is okay. All right, so let's just do one example here, and we're going to save the other two for class. So the first thing that I would do, as it says here, we need to identify our vertical asymptote and our horizontal asymptote. So the first thing I'm going to do here is I'm going to rewrite my function in terms of exponentials. So 6 here is a constant. So I can rewrite this as 6x to the 0 power. X to the 0 power becomes 1, so we're left with just 6. And I can rewrite x as x to the first power. This comes into play for our horizontal asymptote. So first of all, vertical asymptote, what value of x would make our denominator 0? Well, I only have x in our denominator, so that gives it away. That would give me x equals 0. And what I would want to do is I draw this in. X equals 0 is just our y-axis. Now for the horizontal asymptote, that's where we're going to refer back to our chart. So in this case, the exponent of our numerator is less than our exponent of our denominator. So that tells us that y equals 0 is going to be our horizontal asymptote. And I can go in and draw that line as well. So same asymptotes as our last example. Okay. Since these are our asymptotes, we can instantly kind of infer something about our x and y intercepts. We're not going to have any. So I am going to write none for both of those. But we can also show y. For our x-intercepts, plug in or substitute in 0 for y, or f of x. 0 equals 6 over x. And this is never going to happen. because if I multiply to x over, we would just get 0 equals 6, which is not a true statement. Similarly, with our y-intercept, plugging in 0 for x, I would get 6 over 0, which is undefined. So that also will never occur. Okay, I'm going to save domain and range until we've graphed. Just makes our process a bit easier, but I'm sure you guys can assume already. So now let's substitute in our x and y values. So since we have 6 over x, I'm going to choose numbers that divide, well, when you are dividing by 6, divide nicely. I'm going to choose -6, -3, -2, -1, 0, 1, 2, 3, and 6. All right, I'm going to go down the list now. 6 over -6, -1, 6 over -3, -2, 6 over -2 is -3, 6 over -1 is -6. 6 over 0 is undefined, as we found over here. 1 would be 6, 3, 2, and 1. Now I'm going to go ahead and graph these. -6, -1, -3, -2, -2, -3, -6, -1, -6. Okay, once again, I can go through and start graphing my hyperbola. Same goes with the positive direction here. 1 and 6, 2 and 3, 3 and 2, 6 and 1, and once again, I can go through and draw my hyperbola. And that's going to give me a graph that looks something like this. As we can tell, once again, with domain, really, as I head in the negative or positive directions, I'm all good, besides at 0. So my domain is all real numbers, except for that x cannot equal 0. And similarly, with my range, as I head in the negative direction, I'm good. As I head to the positive direction, I am good, but not at 0. So my range is also going to be all real numbers, except this time y cannot equal 0. All right, so that is the general process here. We will save the other examples for class, make sure we work through them together. If you would like a head start on those, you can try both of these on your own, but make sure you come to class with any questions that you have. All right, thanks for watching.